Hello, this is Concrete Path, and today's lecture is for the influence line diagrams related to your trusses and floor girders. So it's that only for we write that as floor girder. So your floor girder is we say uh, it may be used in your bridges. If you have a bridge of that beam bridge, we call that as a bridge made of beam. So the configuration of that bridge looks like you said we have two supports that are two abutments, and on that we have a bigger longitudinal girder. Longitudinal girder is there, and on that bigger girder, longitudinal girder, we have what we call as cross girders. We have cross girders. They are also girders, but we call them as floor beams, or we can also say them as they are cross girders. And the bottom one is your long girder, longitudinal girder, long girder. That's your floor girder, main girder. Then these small girders, they are placed in the cross direction. That's in the transverse direction. And on the top of that, we have those joisters. We call them as joisters or stringers. This is your joist, or we can also call them as stringer beams. Stringers, stringers. They are placed on those what you call as floor beams. So these are your stringers. Stringers. So on the top we might be having some wearing cores. We might be having some wearing cores, or we can have some plates, steel plates. We might have some plates on the top. Let's say that we have a plate on the top. We have some plate on the top. Let's say we have some plate on the top. Let's assume that this is a plate on the top. This is a plate of some small thickness. Let's represent that by some sort of line. Let's say there's some plate there. So on the top we say there's some wearing course, or there's some plate. This is your plate. We can call it as deck plate. So the load from the deck plate, it may be having some UDL concentrate loads. So on that top we might be having some intensity, loading intensity. Let's say there is some load UDL, and that load gets transferred to those what you call as stringers, and the stringers transfer those loads as onto these floor beams, and the floor beams transfer the load as is in the sort of point loads on the long girder. So the distribution is that we say that loading goes from stringers to floor beams, then after to what you call as floor girder. That we also can say we have some cross beam, and we have some main girder. So this is the load mechanism, and after that from the girder we transfer the load to the supports. That's the abutments. That's from the two sides. Maybe two mountain or some hills maybe, or we can have some concrete stuff there. So this is the load mechanism, and we need to draw the ILD for your longitudinal girder. So for this one we need to draw the longitudinal girder, and we have some points. Let's say this is some point A, B, C, D, E. So where those cross beams, cross girders are located, those points we call as panel points. Panel points. We call those points as panel points. That's your point A, B, C, D, E, and we say that the panel shear force, we call that as panel shear force. That's constant. This is the important point from this. This is the important statement from the from this discussion that panel shear force is zero, is constant for your one panel. Let's say any panel you take any panel BC. I would say in this panel shear force is constant, shear force remains constant in the panel BC. Similarly in all other panels also. So so we have to draw the ILD of that. So we say that if you got the ordinates at different panel points, then we can join those by straight lines to get the ILD for your cross girder. We see you get the ordinates, you get the ordinates at, so to draw the ILD, you get the ordinates at panel points. Then after that join by straight line. To get the influence line diagram. So let's take the problem so we can have that. So let's take a problem. We have a girder, cross girder. This is our main girder, longitudinal girder, and it's supported here. Let's say this is support. Let's forget the support. We say that this is 10 meter, this is 10 meter, this is 10 meter, and this is 10 meter. So then after that we have those panel points where we have cross beams. Say this is a channel section, and it's actually in this fashion that we might be having some width where width of the bridge from which where from the loads are coming, that in this way moment of the traffic, we can say moment of traffic. So this is the channel section of that. This is the channel section we have. And similarly at this point we can say we have that I section also. At this point we have one more I section here, one more I section, and one more I section. We can say these are your beams. They are in this fashion. We might be having some width of the road, or width of the, what we can say, bridge. So accordingly we can have that. Okay, so these are your what you call as cross beams. These are your cross beams, and on that top we are showing that directly. We have some deck plate. We have some deck plate, and load is moving. Let's say unit load is moving. In this way, and we need to get the ILD, influence line diagram, for shear force, for the shear in panel CD. Let's say that this is A, B, C, D, E. So we need to get, but we have to get it in the floor girder itself. So in this range, we need to get the panel in the CD. We need to get the shear in the panel CD in the floor girder. That means from this point to this point, we need to get the shear in the panel in the floor girder itself. So we have that 40 meter floor girder beam. So let's have that ILD. So we say we have how many critical points we have. So I would say we have one critical point, 1 point, 1 point, 1 point, 1 point. So 5 loading points. So we say that we are applying loading at those panel points. We are applying loads at those panel points. So let's take the first case, that load at A. If the load was at A, if the load from the top, it was at A, load was at A, there was some channel section. So this channel section would give a reaction of that same unit of 1, and same reaction would get transferred onto this beam. That's your 1, and the total length is 40. Can I get the reactions? If this is 10 meter, this is 30 meter. Can you get the reactions? Can I say this one would be downwards 1/3 of that, and this would be 1 plus 1/3, that's 1.33. Can I say that? If you do summation of moments about any point, and you can accordingly get those values. So once we got this, we need to get the, this means that when load was at point A, what was the shear at the point C and D? Since we say that panel shear force remains constant, that means up to from point C to point D, shear force would remain constant. You can see that from this diagram also. If there was some shear force here, if there is some reaction 1.3, if I cut section somewhere here, I would say what is the shear here? That would be upwards here. That's 1/3 also. Now, once I cut this section, I would say this is upward shear on the right of section. So this is positive shear. So I would say positive value of 1/3 is the shear at section CD when the load was at point A. When the load was at point A, shear in the panel CD was equals to 1/3, that is positive value. Now, if I draw that ILD, I would say when the load was at point A, see, this is the direction of load. When the load was at, this was 1 kilonewton. When the load was at point A, our value of ILD was 1.33 for the, this is the ILD for shear in panel CD. So I would say this value is equals to 1/3, that's 0.33, that is 0.33. So we got one first critical point. Now second one is that when the load is at is directly above that point B. So let's take that point B now. Let's take that point B. If the load is at point B, I would say load was at point B, there was some I section, it would give reaction in this way, and similarly that would get transferred to the beam where we have support, where we have some support. Let's say this is support alpha, so we have some support alpha. So I would say the load transfer mechanism in load path is in this way. So I would say shear at all points is equals to 0. So except at this point, we say you take any points, shear would be 0. Shear would be 0 everywhere. So that means VCD is equals to 0. When load was at point B, shear was 0 at point C also, point C and D. So this is the, that means when load was at point B, shear was 0. So we got the second ordinate also. Now third one is that when load is at point C, when load is at point C, when load is directly above point C, I would say that gets transferred to that I section. This is load at point C, and it would give reaction of 1 also, and same get transferred to that beam. Let's take that beam now. Let's take that beam now. I would say this is some support here, alpha, and there's some one more support, beta, and this is the length, that this is 30 meter and this is 10 meter, and load is acting here. Load is acting here at 10 meter from alpha and 20 meter from beta. So this is the load that's acting here, 1 unit. So if the load is acting 1 unit, so I would say the reaction here, that's closer side, it would be 2/3, and from this side it would be 1/3. It would be 1/3. Now if I cut any section that's if your point is C, that means just after C and just before D, this point and this region is CD. If I cut any section here, I would say there is some section that is somewhere between C and D. This point C, load is acting at that C, but we have to just see just after that point C. So if we cut that section, I would say you are applying a reaction of 1/3, and there is no any external load in the CD part. So I would say you would be having some shear of 1/3 downwards. Now if I see that, what is this as per sign conventions, what is this shear? I would say you have a right of section, your shear is downwards, so this is negative shear. So this is negative shear, 1/3 negative shear, negative 1/3. So somewhere here 0.33. So we got the one more ordinate. Now we have to keep the load at point D. So once the load is at point D, now we can say once the load is at now the load is at point C. Let's say the load is at point C. Your reactions would get accordingly changed. Your reactions change accordingly. Now if the load is at point D, I would say there is some I section, and accordingly then the transfer would be the load finally transferred here 1 unit, and the reaction here would be 2/3, and this one would be 1/3. And if I cut any section somewhere in the CD, see, this is the load at point D. This is the load at point D. So we have to cut just after that. We have to cut the section here. So effect of 1 unit would be also there. So if I have that section also, I would say there's some 1 unit, and we have some 2/3 here. So finally, I would say net value is from the side 1/3 downwards. So I would say upward shear would be 1/3 final value, and that would be positive plus 1/3. that would be positive 1 by 3. Or we can go from this side also. If you got the reaction that's 1 by 3 here, now I cut some section here just before point D. So point D is somewhere here. So I would say the shear here would be equals to 1 by 3 downwards. And if I have that section, that this is your positive shear force 1 by 3, 1 by 3. So here the value is 1 by 3 positive 0.33. Now if the load is at point E, if the load is at point E, there we have some channel section, it would give reaction of 1, and same load gets transferred to the support, that's beta support. So that means shear would be 0 in the panel CD. So shear would be 0. So I would say this is the ordinate. Now we have to join those ordinates by straight lines. And the thing is that the slope should be same. Slope, we have to maintain the slope also. In that fashion, we have to maintain the slope also. So this would be point B would be here. So this is the ILD for your ILD for shear in panel CD. So we got that. So let's say this is positive and this will be negative accordingly. So we have that. If it similarly talk about what you call as a moment at any section X. Now, if you talk about that moment at any section X, let's say that we have that. Let's have main girder. If there is some, if you're talking about that main girder, that's your floor girder. Now, let's say similarly we have one more problem in this way. 1, 2, 3, 4, 5, 6, 7. And we have those joists. Of smaller, we can say thickness also. Thickness is smaller. Let's say these are your joists, and load is moving from the top. Unit load of 1, and on the bottom we have those what you call as floor girder or longitudinal girder. Its depth is usually 1 meter, 2 meter, 1 meter. So it's your girder, long girder, and there is some abutments on the sides. So we are saying that you need to get the shear force at any section X. Shear force, let's take any section, let's say any section somewhere here. Let's say this is your section X, and we need to get the ILD for shear in at that section X and moment at that section X. So one thing is that we say panel shear force is constant. And one more thing is that we are applying loads at the joints. So we need to get the ordinates at the joints. So if you talk about that simply support beam subjected to that any kind of load, what is the ILD for that? We say this is the ILD, that x by L and L minus x by L, negative positive. So now for this one, I would say you take that reference line. I would say now our critical points is that we have those joints. We are applying loads only at the joints. We're applying at these points. We're applying the loads. I would say your critical points becomes that if you're talking about that section that's between two, let's say this is some alpha, this is some beta. So between those two, so our critical points are alpha and beta. So we need to get the ordinates at alpha and beta, and it should have been, if the beam was, let's say it was a simply support beam, and we are talking about that section X, I would say ILD for the shear was in this fashion. And similarly, if I draw that dashed line, I would say ILD would have been in this fashion. It would have been in this fashion, but we are not applying loads on the mid part. We are applying loads at the joints. So your ILD looks like then in this fashion, that there's some critical. So this is our location here at this point, and from this side we have up to this point. So the ILD of this ILD for that shear at that section X is actually in this way. It is in this way. Then we have to join those two ordinates by a straight line. We have to join those ordinates by a straight line. We have to join those ordinates by a straight line. Then this part we can remove. This part we can remove. This part we have to remove now. Then we join those two ordinates by a straight line. So we have two critical ordinates. And if I talk about this value would be equals to x by L. And the slope is actually, we know the slope for the, when we have reaction A, do you know the slope? Total unit was 1 and slope was 1 by L. Similarly, we have the slope here also 1 by L, total L. And if I know, I can get the ordinate here. If I say this is x, I would say this ordinate is also x by L. And if this is let's say this is some A, I would say this is some A by L. And this is some B, I would say this is B by L ordinate. If I extend it, I would get value of 1 up to this point. This is 1 unit. So this is the ILD for shear at section X. This is the ILD for shear at section X. Now, if I talk about that moment at that section X, let's go for that. We know that if we take any section in simply support beam, the ILD at that section is in this way. That's your x into L minus x by L. Actually, it should have been in this way, or we can say AB by L. Now, but the loads are not applied at those between those panel points. We are applying loads at panel points only. So critical locations are those panel points between that section. So I would say your panel, I have to make the diagram in this way. I would say if I extend it somewhere, I would get a diagram. Here the ordinate would be actually x times L minus x by L. And this ordinate, I would say the slope here is equals to B by L, and here the slope is A by L. And accordingly, I can get the ordinates. By the similar triangles, I can get the ordinates. So this is the diagram. Then you have to join those 2 points by a straight line. This is the ILD for moment at any x. ILD in the floor beam, floor girder for moment at any section x. So let's go for problem 1. That is the first and the final problem of the floor girders we have. First and the final problem of the floor girders. That's, we have a simply support bridge. That's 20 meter span. And we have placed two longitudinal girders. And the spacing between those girders is 5 meter. That means we have two girders. And we say that the beams are, we usually design in the form of I sections. So when we have two longitudinal girders, and they are for the length of, what you can say, for the length of L equals to 20 meters. So length from this side, I would say this is L equals to 20 meter. And on that top, we are applying, we are having those cross beams. So cross beams would be in this way. So cross beams, if I say cross beams would be in this way. This is your cross beam 1. Now if I see the cross section, I would say the cross section looks like, this is also I section. Let's say this is also I section, some sort of I section. And similarly, we have one more that cross beam here, and this is also here up to this point. So this is one more cross I that what you can say cross beam or cross girder, we can say. This is your long girder, and on the top we have those what you call as stringers, or we can say joists. Stringers or joists. So let's say we have some joists also. Actually we keep those what you call as, we keep these cross girders up to the center of the beam, up to the center of that section of the long girder. Up to the center of the section, we keep those. You can remove the rest of that. We only keep up to this point, let's say. And then after that, I am applying those what you call as small stringers. They also may be of I section. Let's say they are also of I section. Let's say there's some I section, and we are having those also here. Between they are placed on the top of what you call as floor beams, and on that top we have some deck plate. On the top, and the load is moving in this space. So spacing between those two girders is 5 meter. I hope you got the picture. Okay. And so the problem was that we have simply support bridge 20-meter long, and we have two long girders at 5-meter spacing. Spacing is 5 meter, and we are applying that load of 7.5 kilonewton per meter square. That means if you take 1 unit, if you take 1 meter square from the top, if you take 1 meter square of the plate, deck plate, we can say, if you take 1 meter of that, on that we have this amount of total load acting. So okay, that's your loading per unit area, loading per unit area. Then we say this is your loading, this is your live load, this is your imposed load, this is live load, and we can place it anywhere. Live load can be placed anywhere, can be placed anywhere, place it anywhere. Now what we need to get, we need to get a reaction at A. That means one of the support would be having that, we are having that long girder, and let's say one of the support is here, one of the support is here. So let's say this is AB. We need to get reaction at either of the supports. Let's say that we need to get the reaction A, ILD for the reaction at A, and we need to get shear force at point C. That's at quarter span. That's at quarter span of the from either of the side. Let's say from A, that's your x equals to L by 4. If your L was 20 meter, that means x equals to 5 meter. That means this section where you have to get the shear, that's at 5 meter from the one of the supports. And we also need to get the moment at the mid span. That is your at x equals to 10 meters. So mid moment, bending moment, ILD for bending moment at mid span of the long girder. So ILDs we have to get for the long girders. Let's go. Now one more data was provided to you. That's your we are having cross beams. We are having cross beams or cross girders, you can say. They are placed at 4-meter spacing. 4-meter spacing. Now we have this data, and let's go for the problem. Let's take the problem finally. I would say you have what you call as, you have two floor girders, you have two long girders, longitudinal girders. They are at a spacing of center to center spacing of 5 meter. So if this is the center to center, I would say they are at spacing of 5 meter. Let's say this is 5 meter. And on the top of that we have those cross beams. Let's say this is a cross beam or cross girder. Let's say this is cross girder having a section of, let's say this, we don't care about the section for now. This is cross beam, and on that top we are having some deck plates and that extra part. So let's say that we are having some panels, deck plates or something like that. Let's say we are having some sort of, let's say this is some plates, deck plates or and extra. We don't care about that. We are having that loading on that top. We are having some loading also. Let's say the loading is, we are getting the loading as 7.5 kilonewton per meter square. So I would say that if the loading is in this fashion, that this is your L equals to 30 meter, and we are having intensity in terms of area, so kilonewton per meter square. So intensity is 7.5 kilonewton per meter square for the length of 30 meter. I would say if I convert it in terms of line load, we know we convert that meter square in terms of per meter. If I convert it in terms of line load, I would say there is some net 7.5 kilonewton per meter square loading intensity. Then that would be equals to 7.5 kilonewton per meter square into that width. There is some width of 5 meter. So if I multiply that, I would get that loading intensity of 7.5 into 5. That is equals to 7.5 into 5. That's equals to 37.5 kilonewton per meter. Once I got that loading intensity, that's if I take along the long direction, if I take 1 meter, on that, if I take 1 meter of the, if I take 1 meter, this means that this loading intensity means if I take 1 meter of this 1 meter from along the long direction, and 5 meter from the width of that total width of the of this, what you call as, it may be a bridge. So on this part of the structure, we are having a total load of 5 kilonewton. What is the intensity? 37.5 kilonewton. 37.5 kilonewton. So this is the load on this area, net area. If you take this amount of area, you are having a load of P equals to 37.5 kilonewton. Now, if I take it in terms of line now, I would say that loading intensity is 37.5 kilonewton per meter. Now, we have to ensure one more thing, that the problem was saying we had two long girders. And they are also placed in this way that in the long direction L is some 30 meter. L was given to you. A length was 20 meter. So if there is some loading and we have two beams, cross beams, and I would say they would take half of that total intensity. Out of that total intensity of 37.5, I would say one of the girders, that W on one girder would be equals to 37.5 divided by 2. Can I say that? That means for the calculation for the one floor girder, because we have to draw the ILDs for one of the girders. They are symmetrical, so we need to get one of the girder, and for that we need to take equivalent or effective UDL for that girder only. So I would say by the symmetry, the intensity would be 1 by 2 of that total intensity. Can I say that? So W1G equals to 18.75 kilonewton per meter. Now, finally, if I analyze it for a separate problem, if I analyze it for a separate girder, I would say you have a girder of L equals to 20 meter, and we are having some intensity, loading intensity of W1G equals to 18.75 kilonewton per meter, and we are having some, what you call as, we are having some floor beams, and the spacing was mentioned that floor beams were spaced at 4 meter. It was mentioned that cross beams are at 4 meter spacing, so we have to carefully check that also. 4 meter spacing. So cross beams are to be placed at 4 meter spacing. Let's say this is some support A, this is some support B abutments. So I would say one of the, what you call as, floor, that cross beam would be here. One of the cross beam would be here. So I had to ensure that the spacing between the girders is cross beams is 4 meter. If I say 4 into 5, that means 5 times 4, 4 and 4. That means one of the cross beam would be here. One of the cross beam would be here. One of this would be here. One of that would be here. So we got finally 3 3s are 6 cross beams. 6 cross beams at the rate of spacing equals to 4 meter. So finally we got this one, and on the top we can have some plates. It's not that issue. We have some plates. We have some plates extra, because we are talking about that, what you call as, girder. So we have to draw the ILD for that girder. Now for this girder, the problem is saying get the reaction A. Can you have that reaction A? What is the ILD? ILD for reaction A. If you have a simply support beam, reaction A ILD is some sort of that. You remove that support and apply 1 unit displacement in the direction of that reaction, and by keeping the support beam intact, so this is your ILD that has been developed. So we need to get the reaction A. Reaction A would be equals to, what is the reaction A? That's equals to, I would say, if I place this this loading intensity for the entire part, if I place this loading intensity for the entire length, so I would say if I apply this loading intensity for the entire length W1G, that means I would say what is the reaction here? I would say that's equals to area under the UDL, that's 1 by 2, length of 20 meter, ordinate of 1 meter, ordinate of 1 into UDL intensity of 18.75 kilonewton per meter, and I can get the reaction A, that's 187.5 kilonewton. Reaction A. That's the reaction A. Now if I take that, I had to get the shear force, only for shear force at quarter span. Second part of the problem is that I had to get the shear force at quarter span. That's at x equals to 5 meter. Shear force at the quarter span. Now if I take this beam, if I take this girder, I would say this is a simply support beam. You can say your girder is a simply support beam with a length of 20 meter. Now I would say, why is the 5 meter from A? If I had to go to 5 meter from A, I would say this is some 5 meter from A, 5 meter. So this is your section that you can call as, I can say this is ideally for shear force at point C, that's at quarter span from point A, support A. So for that, do you know the what is the ILD? If there were no panel points, I would say the ILD would have been in this way, that this is 5 by 20 and this is your 15 by 20. ILD would have been in this way for the shear. But because there are panel points, so we have to get the ordinates at panel points. Then after that, we have to join by a straight line. I would say at this panel point we are having some ordinate, and after that at this panel point we are having some ordinate, and slope we know this is 1 by L and this is also 1 by 20. So then after that we have to join those by straight line. So this is the ILE for your shear at 5 meter from support A. Then I would say this is 4 meter, this is 4 meter, and 5 meter would be somewhere here by the symmetric triangles. You can get the why the section 5 meter was, and I would say from this side this was equals to, if this is 4 meter up to the point, this is 4 meter, and up to this there are one more 4 meter unit. After that we have 12 meter from this side. This is 12 meter. Now I need that shear ILD for shear. I would say ILD for shear. Why is the problem? Now the thing is that problem is saying you have this live load, and it can be placed anywhere. I need to get the shear at quarter span. So for the shear, if I say I want to get the shear that's maximum. If I want that, I want shear that's maximum. It can be positive or it can be negative. It can be positive or it can be negative. Shear at C to be, I want shear at C to be maximum at the quarter span. So that means I have to place the that live load in a way such that I can get a maximum shear force. I can get a maximum shear force ordinate values. So I have to place that live load in that way. So if I see this diagram, if I see this ILD diagram, influence line diagram, I would say your positive area is more. Now if I want that, I would say V negative at 5 meter would be lesser than V positive at 5 meter. Can I say that? If I place load in the negative part, only, I would get a V negative that's lesser. Now because your area under the curve, under the UDL for the positive side is more, I would say V positive would be more. Let's take that now. I would be solving that V positive maximum, and that would be V that is ILD for shear, and finally I would get shear at that point, quarter span section. Let's take that positive side. I would say we have this what you call as area. Can you get this ordinate? Can you get this length by the symmetric triangles? Can you get this ordinate? If this is 12 meter, what is this value of? What is this value equals to? And what is the ordinate here? Can you tell me what is the ordinate here? Can you tell me what is the ordinate here? I would say this ordinate is that we have 12 by 20. Can I say that this is 12 by 20? And by the similar triangles, this one would be equals to 4 by 20. Now I would say 4 by 20, that's 1 by 5, that's 0.2, and this is 12 by 20, that's 3 by 5, that's 0.6. I would say 0.2 is for the length of 4 and 0.6 is for the length of Yeah, I would say from this strength, let's say this is some value of x and this is some value of y. This is some value of x and this is some value of y. I want to see whether your section is exactly at the 5 meter. I want to see what is this value of x. I would say your value of 0.2 0.2 is for the length of x, and by the similar triangles, that's this length is equals to y, and value of y is equals to 4 minus x. Now if I solve that, I would say 0.8 equals to 0.6 plus 0.2 x. So x equals to 1 meter. That means x equals to 1 meter. If this is x equals to 1 meter, that means total length is 5 meter. So that is the section at C. That's the quarter span. So we are getting shear at this point equals to 0. That's if the load was at this point, shear would be 0. Shear would be 0 at that point. That means if the unit load was exactly at this point, I would get a shear equals to 0. So finally, I got that. Now I can say this is equals to y. That's 3 meter. Now finally, I got that. I would place that UDL live load for the entire length. I would say the V positive, that's maximum at point C, that's equals to 1 by 2, 15 meter, and ordinate of 12 by 20, and UDL of 18.75 kilonewton per meter, and your shear would be equals to 84.4 kilonewton. Now the third thing is that moment at ILD for bending moment at. First we need to draw ILD for bending moment at the midspan. Then accordingly we need to get the bending moment at midspan. We need to get then finally bending moment value at the midspan of the long girder. Let's go for that also. Let's go for that also. Let's go for that. So this is the reference line we have, and after that I have to ensure those critical points. Let's say that support that section midspan is, if this is 4 meter, this is 4, and total is 20. That means 4 plus 4, 10 meter would be somewhere here. 10 meter would be somewhere here. 10 meter would be somewhere here. So if I say that this is your section, and we need to get ILD at midspan, moment at midspan. Then accordingly, I would say we have two panel points. One is your panel point 1, then is your second one. So at that point we have some ordinate here, and from this side also we have some ordinate. And by the symmetry of that, because we have symmetry, our ordinates on two sides would be same because of symmetry. Because our section is at midspan. That means this ordinate and this ordinate would be same. This ordinate and this ordinate would be same. They would be equal. Now if I have that, I have to join those by a straight line. I would say these two values would be same. This peak ordinate would have been AB by L. This would have been 105. This would have been 5 for the length of 10 meter. And if this length is 8 meter, I would say ordinate here would be equals to 4, and this ordinate would also be equals to 4. Now I want that bending moment to be maximum at 10 meter, to be maximum. How can I place the live load? I would place the live load for the entire length, because we have that diagram that's entirely positive. So this is entirely positive diagram. So I would say you place the load for the entire diagram. I would say the area under the curve, that's 1 by 2 sum of parallel sides. So that's your this one. What is this length? Can you tell me what is this length? Is this 4 meter? I would say this is 4 meter. And what is the total length at the bottom? I would say this is 20 meter. So 20 meter. This is the sum of parallel sides, and we have to multiply that ordinate of 4 meter. This is the 4 meter ordinate. Okay. Then we have to multiply that intensity also, 18.75 kilonewton per meter, and you can get the bending moment. That's equals to 900 kilonewton meter positive. So that was the end of the floor girders. That is the end. That is the end of the floor girders. Thank you.